All right, so let's get into it. So again, we are in this situation where we have a function f of x. It is centered at a point. Typically, we've called this x equals a for bad notation reasons, I guess. I called it x equals c here, but a polynomial f of x centered at a value, and it's going to be given by this formula. I should say the Taylor polynomial is given by the formula up above, and the remainder formula is going to be just the function itself minus the nth degree Taylor polynomial. So the remainder is this leftover piece. It's the difference between the function and the polynomial. If that's the remainder, then the error of the polynomial is going to be the absolute value of that remainder. And we'll notice that both the remainder and the error are defined in terms of x, right? So they're both functions. At a given point x, the remainder is the difference between the function at that x value and the polynomial at that x value. And then the error is just the absolute value of that. So it's important to us to understand what is this error and how bad can the error get. And so there's actually an error formula, which it's a complicated little formula, and we ultimately don't care that much about it. But for completeness' sake, I wanted to include it here. So we are, again, this is the remainder. This is the difference between the nth degree polynomial and the function itself. The remainder turns out to be, it'll be 1 over n plus 1 factorial times the central value, whatever that is. So that will be, I guess, c, well, let's say it like this, x minus c to the n plus 1, right? Again, c, this is where we're centering our polynomial around, and x, that's whatever x value we're looking at, right? That's the same x value as over here. So it's 1 over n plus 1 factorial times x minus c raised to the n plus 1 times the n plus 1th derivative of the function at some other point at u for some u value near c. Specifically, I guess I'll be even more specific. So for some u value in the interval between x and c. So what a messy formula. I feel better about myself for not remembering it last time. That's a gross looking formula. Let's talk about the important takeaway message, because again, I don't actually care that much about this formula. What I care about is that the remainder is something that we can explicitly compute. What's sort of weird about it is that all of this is fixed except for that u value, right? The idea here is that there is some u value in the range for which this equation is satisfied. And this should feel similar to us, or this should feel of a similar kind of statement as something like the intermediate value theorem or the mean value theorem or an average value from earlier this semester, right? What we're really saying is that if we're interested, here's the point where our x value is centered, or I'm sorry, where our polynomial is centered. Here's our c value. Here's the x value where I'm estimating the error. What I'm claiming is that that error can be rigorously estimated by some formula involving some u value somewhere there in the middle. So there exists a u value at which I plug that into the formula and I get that that is directly equal to the remainder. So again, similar flavor to the average value theorem or the mean value theorem for integrals, the idea that there exists this average value or this point somewhere in the middle that can represent the average value. But messy formula, we don't care that much about it. Here's what we do care about. Because we have this estimate, and the sort of weird point is this U value, right? We don't necessarily have a good way to find the U value. We're just guaranteed that it exists somewhere in this range. One thing that we can do is we can say that whatever f to the n plus 1 of U is, right, even if I throw on absolute values, that will still be less than or equal to the maximum value over all of these different potential U values. So we're going to say that this is less than or equal to M for some M value. And that is what we end up using down here. So again, we had a messy formula. It's a bit of a pain, but we end up saying that whatever this value is, we can find some M, some capital M that's bigger than it. And notice that's exactly what we did down here. And that means that the remainder, and therefore the error of this polynomial, is going to be bounded by the same expression, right? So 1 over n plus 1 factorial times the x minus c to the n plus 1 times, and then I'm just going to replace this piece with this upper bound m. And that's what gives us this formula down here. So in essence, we can not ignore, but we can set aside and probably forget about forever until the next time I teach this class. We can forget about this particular remainder theorem and focus on this error bound down here. And that's where we really ended class last time. So that's what I want to return to. I'm noticing, I think there was an error in my notation last time. I have, oh no, this is okay. It's just between A and C. So again, this is an issue of bad notation. This is an issue of bad notation. I think we're sort of confusing potentially the role of A and the role of C as two potential X values. One of these is the center of the Taylor polynomial, and the other one is the place where we're estimating the error. All right, so let's get into how we actually use this, right? Because anytime we are doing some sort of estimation or an error bound or something, it becomes a real pain to work with. So let's try to figure out how we actually do this. We're going to take a look at problem 8, find an n value such that p sub n of 1 minus e is less than or equal to 10 to the negative 6, where p sub n of x is the Maclaurin polynomial for f of x equals e to the x. Okay, great. So let's see what we got going on here. So first of all, let's make sure we understand what this question is even asking. We have our polynomial, right? So we have our Taylor polynomials, our Maclaurin polynomials, and remember our Maclaurin polynomials are centered at 0. So we can calculate the first several of these, right? And as a reminder, we would have p sub, well, let me write these down and then we can verify that these are true. We would have p sub 0 of x, the 0th order Taylor polynomial is just 1. The first order Taylor polynomial for e to the x is 1 plus x. The second order Taylor polynomial is going to be 1 plus x squared over 2. The third order is going to be 1 plus x squared over 2 plus x cubed over 6. And the nth, more broadly, the nth order Taylor polynomial is going to be the sum as k goes from 0 to n of 1 over k factorial x to the k. So that's the pattern that we're seeing here. Now, this was something that we derived in class last time. It was one of our earlier problems. Specifically, Zoom, zoom. Oh, this was one that we did. Yeah. This was problem 5 from before. So these are our Taylor polynomial approximations around a equals 0. Now, what we're asked to do is to use these to approximate the number e. In other words, each of these are approximating e to the x, f of x equals e to the x, and we want to use these to approximate just the number e by itself, aka e to the 1. So we're interested in taking e to the x, plugging in x equals 1, and approximating it using an appropriate Taylor polynomial plugged in, again, at x equals 1. So in other words, we are going to compute the error p sub n of x minus e to the x. This is the error term. And we're going to try to compute this, or maybe estimate it is a better word. We're going to try to estimate it, specifically at x equals 1. We're going to use our error-bound formula to do this. So let's give this a try. According to the formula, by the error-bound formula, we have p sub n of 1 minus e to the 1 in absolute value is going to be less than or equal to, and now it's going to be n plus 1 factorial in the denominator. And in the numerator, it's going to be an m, some capital M, TBD, times. And then we have this expression, we wrote it up there confusingly as a minus c to the n plus 1. This is just going to be our central value in the estimate minus the actual value we're interested in raised to the n plus 1. So in this case, that's going to be, well, we're centered at the number 0. And we're interested in estimating this at x equals 1. So this is really just absolute value of 0 minus 1 raised to the n plus 1. Okay. So what is this m value? What is m? Sort of as a side, well, sort of side quest, right? As a side adventure here, we have to understand what m can be. And we'll do that sort of off here on the side, Gesundheit. We'll do that off here on the side in blue. So m is an upper bound on the n plus 1th derivative of f of x on the interval of 0 to 1. Maybe make those hard brackets to include the endpoints. Right, so again, this idea that we had was that this m value is supposed to represent an upper bound. It's supposed to be larger than any possible n plus 1th derivative of our function. So what we have to do is we have to look at our function, figure out what the n plus 1th derivative is, and then see how big that can get on the interval 0 to 1. So let's take a look. Again, the function that we're looking at is e to the x. Thankfully, the n plus 1th derivative of e to the x is just e to the x again. And so on 0 to 1, how big does e to the x get? Right? So if we want to, we can use technology to help us out here. We can also just sort of do a thought experiment to help us out. But if we use technology, the n plus 1th derivative is e to the x, or the n plus 1th derivative of e to the x is e to the x. So here's e to the x. We're interested in e to the x being between 0 and 1, and we're wondering what is the largest value this achieves? Well, the largest value happens to be on the right endpoint. It happens at 1. The largest value is just e to the 1, aka the largest value is e. I don't know why it said undefined there. Oh, it's because I made this just a strictly less than. Yeah, it is e, aka 2.7 something something something, whatever e happens to be. So a good upper bound for e to the x is e to the 1. So m equals 1, I'm sorry, m equals e is a good choice. Okay, so with that side adventure mostly complete, we come back here and we say then that the error we were interested in estimating from the beginning, the p sub n of 1 minus e, is now less than or equal to this m value. We said that e was a good choice. The 0 minus 1 in absolute value to the n plus 1, that's just going to equal 1. And in the denominator, we have this n plus 1 factorial. So this is great. This tells us how bad or how big of an error we can expect from our nth degree Taylor polynomial if we wanted to approximate e. It tells us specifically that the difference would be, less than or equal to, the error would be less than or equal to e over n plus 1 factorial. And now we asked the question, going back to the beginning, we wanted to see what n value would let this be less than or equal to 10 to the negative 6. Right? So the question is, what n value will make this quantity less than or equal to 10 to the negative 6? 10 to the negative 6 is a... So as a final step, we could say 10 to the negative 6, that's going to be 0.1, or 1, 2, 3, 4, 5, 1. Did I do that right? Did I do that right? That's 10 to the negative 1, 2, 3, 4, 5, 6. Maybe that's right. 1, 2, 3. Yeah, a decimal point followed by 5 zeros. Cool, okay. So this is 10 to the negative 6. Our question was, when can we make this quantity less than 10 to the negative 6? This error bound leads the way. If we know that this quantity is less than 10 to the negative 6, then because of this inequality here, the error would also be less than or equal to 10 to the negative 6. So our goal becomes to find an n value for which this is less than 10 to the negative 6. And for this, we're just going to use technology for sure. No reason not to. Oh, did you see the Google Doodle today? Is Mandelbrot, mathematician who created fractals, or who first like really dove deep into fractals. I think it's his birthday today or something. It's his 96th birthday today. 3 times. I don't know. I think he's dead. I think he's dead. I don't. Okay. It's like, I should know this. I should know this. And also I'm recording myself right now. So if I don't know, it's going to be up on the YouTubes forever. Okay, so what were we doing? What were we just doing? Yeah, fractals are tons of fun. Mandelbrot did a real interesting, sort of study of them and really brought them to the forefront. You might have heard of the Mandelbrot set as a really interesting fractal set. Anyway, just a fun thing to look at over a cup of coffee at some point if you're interested. We were interested in calculating e divided by n plus 1 factorial and seeing for which n value that became less than 10 to the negative 6. So e divided by n plus 1 factorial is in tight. Let's try 2 plus 1 factorial. So that's, again, e divided by 3 factorial. That would be e divided by 6. That's definitely too big. 3 plus 1 factorial, 4 plus 1. Ooh, okay, we're starting to get a little closer. So 6 plus 1 factorial is not quite big enough. 7 plus 1 factorial is not quite big enough. That's 1, 2, 3. 8 plus 1 factorial is almost there. That's going to be that's going to be a 0.000007. And there we go. E to the 9 plus 1 factorial is small enough to be under that error bound that we were interested in. So e to the 10 factorial, e to the 9 plus 1 factorial. So we can note, sort of using technology, if n equals 9, we saw that this expression was less than or equal to our calculated error bound, right? Maybe I should say if this is p sub 9 of 1 minus e, that's less than or equal to e to the 9 plus 1 factorial. And by using technology, we saw that that was less than or equal to 10 to the negative 6. And again, to highlight something that we talked about last class, this is how our actual calculators calculate decimal approximations for the numbers that we know and love, or kind of love, things like e or things like pi, right? It can set up a Taylor polynomial. It can do a quick calculation, maybe find some error bound to learn how many decimal how big of a Taylor polynomial we need. And then it can compute the Taylor polynomial to get the decimal approximation. So if we had a calculator that only had 6 decimal points, or like 6 points beyond the decimal, and we asked it to calculate e, this might very well be the approximation that it uses to compute e for us, because it would be indistinguishable on our calculator out to 6 decimal points. And even though this is a 9th degree polynomial, which seems massive and annoying, it is far easier for our calculator to work with that than to work with some weird transcendental number like e. So A fun side adventure in numerical approximation, which I know is everybody's favorite topic. Any questions about this? What questions do you all have about this? Yes. Yes, yes. That's a great question. So the question, to repeat it, was that does the interval that we looked at, I'm guessing in this case, the interval 0 to 1. Whoops. The interval 0 to 1. The interval is coming from the A and C values. So again, it's coming from these values up here. So in particular, in this case, we centered our polynomial at 0. We were interested in using it to estimate the height of 1. And so that really became the interval that got used both in the formula for the error bound and in the interval for figuring out what m should be. Yeah, great question, great question. So that interval sort of plays a double role. It plays a role up here, and it plays a role in figuring out what m should be down here. Yeah.
What are the m values? Is it the absolute max, or is it just the upper bound?
Yeah, this is another great question. Thank you. The question was about the number m. Does it have to be this absolute maximum, or is it just some upper bound? It can absolutely just be some upper bound. So we chose the maximum value, which is the least upper bound. It's the smallest of all the upper bounds. But we didn't have to do that. So we could have been a little lazy. And in fact, we often like to be a little lazy. Notice we said down here that this gets as big as e to the 1. So m equals e is a good choice. I don't actually like working with e that much. One of the big reasons I'm doing this is so that I can try to figure out what e even is. So using it in my estimate seems sort of annoying. So one thing I could do is I could say e is 2 point something. That's less than 3. So if m equals e is a good choice, m equals 3 is also a good choice. It just has to be some upper bound. It doesn't have to be that least upper bound. M equals 10 is also a great choice. Maybe even a better choice because 10 is a nice round number. So as long as I'm verifying that my number in question is bigger than any value of the n plus 1's derivative on the interval in question, I'm okay. So m equals e, m equals 3, m equals 10 would all be excellent choices here. But m equals 2 wouldn't work, exactly, because m equals 2 was not bigger, the height of 2 was not bigger than the height of all of the n plus 1's derivatives. Yeah. So these kind of considerations on finding these upper bounds and finding a good upper bound that also makes your computation easier, this is sort of in the realm of either a course in real analysis or numerical analysis, when you sort of try to work to understand how you can perform these computations, how you can do it in a sort of algorithmically efficient way. Maybe the number 10 would not give me as close of an error bound, but it's easier to work with for me personally computationally. And so that's something that we can consider going forward. So all of this and more in fun future math classes. Any other questions? These have been great questions so far. Any other questions? They don't even have to be great questions. Any questions at all? Great question. Question was, do we have a quiz today? Yes. My goal is to give you a quiz today because if I didn't give you a quiz today, I'd have to give you a ton of quizzes next week or right after Thanksgiving, and that seems even meaner than giving you a quiz today. So yes, quiz today. Hasn't been posted yet, but will be posted after class. Other questions? All right. Well, let's go ahead and move into, I'm going to back out of this sheet and move into the next sheet, which was our sort of bigger goal for today. And this was going to be the sheet on Taylor series. Backing out. Taylor series. Okay, so like I said at the beginning, this is not something that we will actually be able to complete in class today. This will also be the bulk of the class on Monday. But Taylor series are sort of a culminating moment in the course, and a culminating moment for the last week. As a reminder, on Monday, we looked at power series. These were infinite series that involved a variable x. And we talked about how we could interpret them using radii of convergence and intervals of convergence. Then we talked about Taylor polynomials, which were not infinite series. These were finite polynomials of degree n, in which we could calculate errors and fun stuff like that. Taylor series is the natural joining of these two topics. A Taylor series is going to look like a Taylor polynomial, except instead of going up to degree n and then stopping, it's going to go all the way up to infinity. Right? So a Taylor series is going to be, I guess I'll write it up here. Write it up here. A Taylor series for a function f of x centered at a point A, centered at A, has a Taylor series representation of, and now it's just going to be the same formula that we used for our Taylor polynomial. It will be the nth derivative, I guess maybe the kth derivative, evaluated at our center point A, divided by k factorial times x minus a to the k. And now in a Taylor polynomial, we did this as a sum as k goes from 0 to n. Now for a Taylor series, we're going to do this as a sum as k goes from 0 to infinity. So it's going to be, you know, the nonstop Taylor series party here. And this means that we can think about both function approximation, the way that we did for Taylor series, Taylor polynomials, and we can think about radii of convergence, like we did for power series. And we end up with this powerful theorem that says if a function f has a power series representation in A, given by or has a power series representation of A, given by this Taylor series formula, and if the function is defined in this way, Gesundheit, if it's defined in this way for values that are within the radius of convergence, then the coefficients of that power series are given by the Taylor polynomial coefficients. In other words, those C sub n's right there are given exactly in this formula here. So in other words, a Taylor series is a way to represent a function within the radius of convergence. And not only is it an approximation, right, the way that a Taylor polynomial was an approximation, but inside the radius of convergence, the function is equal to its Taylor series. There is no error. So the series in this theorem is called the Taylor series of the function. And again, we talked about Taylor polynomials versus Maclaurin polynomials. When A is equal to 0, this is known as a Maclaurin series. All right. So we have done some of these in the video, but I want to revisit these because I think it's important to sort of think through this process, and because we've laid a lot of the groundwork already. So Maclaurin series, again, that's centered at A equals 0. if we want to find the Maclaurin series for sine of x or the Maclaurin series for e to the x, we can do so going through the exact same steps that we did for our Taylor polynomial last time. So again, we would calculate the first several derivatives, right? And you know what, let me be a little lazy and do the e to the x one, which is a little bit easier. We can revisit the sine of x one here in just a second, but maybe it makes sense to start with e to the x. For e to the x, we had, f of x equals e to the x, f prime of x equals e to the x. You can see why this one is the slightly lazier one. F double prime is also e to the x, and so on. Because this is a Maclaurin series, we are centering this at x equals 0. And so we get f of 0 equals e to the 0, which is 1. F prime of 0 equals e to the 0, which is 1, and so on. And so when it comes time to find our Maclaurin series, the general formula for a Maclaurin series is given by this sum, infinite sum, as n goes from 0 to infinity of, and then we had the nth derivative of the function at 0 divided by n factorial times, again, because it's centered at 0, this is just x minus 0 raised to the nth power. Right, that formula would be true for any Maclaurin series. In the specific case of e to the x, this becomes the same infinite sum. The nth derivative at 0 is always 1, so this always becomes 1 over n factorial times x to the n, as n goes from 0 to infinity. So this is our Maclaurin series for e to the x. But this is also a power series, right? A power series has the form, coefficient out front times x minus a to the n, in this case, just x minus 0 to the n. So this is a power series. Power series have radii of convergence and intervals of convergence. And we could ask ourselves, what is the interval of convergence for this? And if we compute this, our ratio test for the radius of convergence, the ratio test would suggest that we want to see where this converges. We take the limit as n goes to infinity of our n plus 1th term divided by our nth term. And so that's just going to be equal to, again, limit n goes to infinity. Okay, we got 1 over n plus 1 factorial, x to the n plus 1, divided by 1 over n factorial, x to the n. But this simplifies down so nicely, right? As these ratio tests tend to do, this simplifies down. We get a n factorial over n plus 1 factorial times an x to the n plus 1 over x to the n. And each of those additionally simplify down. So we end up getting, do it up here, the n factorial divided by the n plus 1 factorial. That just becomes a 1 over n when all the dust settles. And the n plus 1, x to the n plus 1 over x to the n, that just becomes a single copy of x when the dust settles. So the whole thing becomes the limit as n goes to infinity 1 over n times x. 1 over n times x. And no matter what x value we're looking at, even if we're looking at x equals 1,000,000 or x equals negative 1,000,000,000, as n goes to infinity, that denominator eventually wins. In other words, this limit is equal to 0 for every x value. And so what does that mean for us? Well, if this limit equals 0, we said that meant that the series converged. And so we're saying that this series converges for every x value, right? We plug in an x, the power series just becomes a regular series with an x plugged in, and that series converges. And by our theorem at the top of this page, it converges to e to the x. In other words, the radius of convergence, this, in other words, the radius of convergence for this is infinity. Every single x value, or for every single x value, we can calculate e to the x using this Taylor series approximation. And I shouldn't even say approximation. We can calculate e to the x perfectly using this Taylor series. Fun times, fun times. Okay, I want to end class today. I want to end a few minutes early, but I want to talk through a handful of important Maclaurin series before we go. We're going to, let me see what we can remember here. So the e to the x we just calculated. This was 1 plus x squared over 2 plus x cubed over 6 plus ... AKA, this was the sum of 1 over n factorial times x to the n. The two that I want to focus on the most are our sine and cosine expressions. Sine of x, right? This was the one that we skipped over up above. I will point out, skipped over it up above. I'll write out the first few steps here, right? And this should feel a little familiar, that f is sine, f prime is cosine, f double prime is negative sine, f triple prime is negative cosine, and so on. And so if we're plugging in zeros for x, right, if we're creating a Maclaurin series, we're centering it at 0. And so for each of these, we would get f of 0 is sine of 0, f prime of 0 is cosine of 0, f double prime of 0 is negative sine of 0, f triple prime at 0 is negative cosine of 0. And then those coefficients are going to repeat themselves, right? So in our formula, we would end up getting a 0, 1, a 0, a negative 1, 0, 1, 0, negative 1, all divided by the appropriate n factorial. So what does that mean when it comes time to write a formula for this? Well, we saw there that we actually ended up, I wrote a 1 here, but this should really be a 0 to kick things off. Sine of 0 is 0, so this became a 0 plus x plus 0 minus x cubed. We'll say 0x squared over 2 minus 1/6 x cubed minus 0 plus 0, x to the fourth, etc. To write this out in a more concise way, zooming in here, this is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, and so on and so on. This is exactly the formula that we used when constructing our Taylor polynomial approximations for sine in Desmos last time, only this time the approximation will go on forever. Cosine is going to be the exact opposite of that, right? So with cosine, we'll have that the even terms exist. So the 0th term exists. The x squared term exists. The x to the fourth term exists, and so on. And there's a really fun insight we can have at this moment. Sine, we said way back in the day, was an odd function, right? Meaning that it exhibited odd symmetry, right? So as a reminder, odd symmetry is 180-degree rotational symmetry. And cosine is an even function. It exhibits even symmetry. So it exhibits this reflectional symmetry. What we realize is that the reason these are called odd symmetry and even symmetry is because they are typically seen in the odd functions, odd polynomials, and even polynomials, right? So x to the first power has odd symmetry. X cubed has odd symmetry. X squared has even symmetry, that reflectional symmetry. What we see here is that an odd function, like sine, is being represented using a Taylor series that only has odd terms in it. And cosine, an even function, is being represented using a Taylor series that only has even degree terms in it, right? Especially if we consider this 1 to be an x to the 0, which we should. So we have this amazing, sort of pattern here that reflects something that we fundamentally know about the sine and cosine function. All right. And I think we should probably stop there for today. I'm keeping an eye on the time. We have about 5 minutes left, but I wanted to end with a couple quick debriefs as we sort of pivot to the next stage of the semester. So let's go ahead and pause it there. Maybe I should ask, before we do, any questions? What questions do you all have about this? All right, so let's pause there.